few other natural causes of climate change that we need to be aware of and address. These three big ones are volcanic activity. And a lot of people talk about volcanic activity being significant in actually causing climate change in the positive, where we're warming the planet, or negative in that they're cooling the planet. And in both conditions, or both are right. But the volume of matter that's being emitted from the many, many, many volcanoes that are constantly erupting on the planet is very small compared to what has erupted across geologic time. We're adding a significantly small amount that really isn't changing the temperature of the planet significantly at any given time, unless you've got a significant eruption that will take place. And in 1992, Mount Pinatubo was one of those eruptions. And it erupted enough matter that actually cooled the planet for 4 years. But 4 years is not a long enough amount of time to generate long-term climatic effects that are going to be significant to the well-being of the planet's ecosystems. Greenhouse gas concentrations are numerous, and most of the greenhouse gases are natural in form. So carbon dioxide does happen naturally, methane does happen naturally, and those two big ones, along with water as a third, do have input and output rates that are independent to some degree of human activity, like the cycling of methane out of deep ocean bodies. So those can be significant, and they will have long-term effects. And the homework discusses greenhouse gases, and in particular CO2's long-term effects on the atmosphere. So I will leave you to that homework a little bit without getting too far into the weeds with that one. Ocean cycles also have long-term effects, and these are really, really interesting. We can look at ocean salinity and ocean current cycles and how they change with ocean volume. So when, for instance, we start to melt snow or melt glacial ice into large ocean bodies, we reduce the salinity of those ocean bodies. Reducing the salinity of those ocean bodies reduces the heating capacity of storage of those water bodies. So we actually start to cool off those oceans, and we start to get a feedback effect, right? That we're going to talk about, or I'll talk about here in a moment. So you've got those sorts of conditions happening as the transfer of water to increase or decrease salinity or ocean chemistry. Rising and lowering of ocean volumes also changes the currents, and those currents, as we've talked about, are the conveyor belts to water and energy to higher and lower latitudes. So if we terminate or we abbreviate any of those big conveyor belts, then significant portions of the planet may not receive warm water or may not receive cool water as a result. And then those areas, depending on what the configuration of our planet is over time, and it hasn't always been what we see today with North and South America being on top of each other, and Asia is fused to Europe, and with Africa and India in the southern hemispheres. That's not always been the configuration. But those configurations, as they change, will change also those conveyor belts of what bodies of the planet get what volumes of energy that are cycled. So when we think about then human-induced warming or climate change, what we're seeing is an increase of greenhouse gases, particularly carbon dioxide, with the incomplete combustion of fossil fuels at the start of the Industrial Revolution. And these are measurable. We are able to measure these over time directly and with proxy data. So again, we're looking at carbon dioxide and methane, and then halocarbons, which are compounds that humans have created. And again, the homework that I'm asking you to do addresses this, so I'm not going to get into the weeds very much with it. And I suspect that you've gotten a lot of this in your K-12 education, so that's nothing new to you, or should not be anything new to you. If it is, please come and talk to me. All right. As we're getting close to the end here, I want to introduce two acronyms, GCMs, which are Global Circulation Models, and the ICCP, the International Panel of Climate Change. And the ICCP has helped produce global circulation models, although not all global circulation models are produced and supported by the International Panel of Climate Change. And that's really important to note, because part of what happens with science is that the scientists working on these studies work independent of each other. And they do that to reduce influence. The independence is really important. So scientists that are working with the International Panel of Climate Change and independent of them, that produce mathematical models to understand past climate change and predict future climate change, are able then to take their models and compare them to each other and to test each other's models. And some of the things that they're looking to test and understand is what happens when we increase cloud cover at the equator. What will happen to the temperature under the cloud mass at the equator? How will that result in generating more storms like hurricanes and typhoons? What happens if we see a great reduction in albedo at the poles, particularly the North Pole, because there isn't a land mass to support the ice, so it's going to melt a lot quicker? How will that change ocean currents and ocean dynamics? What areas will get warmer faster? So those are just a couple of questions that the global circulation models help to address. And for us, having seen this particular model a couple of slides ago, not a slides ago, but a couple of units ago, with these Hadley cells and this atmospheric circulation, a big part of the climate change models recognize that we're going to get shifts in these Hadley cells. So here are these Hadley cells right here, and that we've got these feral cells up here, and then there are polar cells. What's going to happen is, as the planet warms, these Hadley cells are going to start to rotate faster, and we're going to see shifts in them. So we're going to generate more cloud cover. More cloud cover means we're going to transfer more clouds to new locations. So we're going to get shifts in temperature, and we're going to get shifts in seasonal moisture. So some places are going to get wetter, and some places are going to get warmer, because we are adding more energy to these Hadley cells, and they're going to put and transfer energy radically different. So I specifically have a question in your homework that addresses this. So I want you to read it and look at it and understand it. All right, guys? If you don't, please talk to me, all right? I want to hear from you. Two more slides. So with albedo change, the big reflective areas of our planet are our poles. One pole has more reflective capability than the other, and that's the South Pole, or Antarctica. And that's because the ice sits on a landmass. And because it sits on a landmass, does not readily melt because of the warm water or the energy afforded by liquid water beneath it. So what we've got is a greater loss of polar ice seasonally in the North Pole. And over time, because the ocean bodies are warming, we're seeing less and less snow and ice formation at the North Pole, which is going to change all those ecosystems that are in the North Atlantic, in the North Pacific, across the Bering Sea. So we've got, this is a pretty old image, but it's actually one of my very favorites. So this nice red line is where the sea ice was back in 1979. Now this is a 2003 image. This sea ice is radically changed since then, and we've got periods where we've got just about an ice-free North Pole. If you're looking economically, then all this area is great for navigation back and forth. It cuts down travel time for exchange of goods and services. It opens up this part of the world for exploration for oil and gas and other minerals in that ocean body, in the Arctic Ocean. But for the most part, we've lost a big reflective lens. And if we lose that reflective lens, we know from albedo that the temperatures are going to go up. And they're going to go up in the summertime when the northern hemisphere is facing the sun. So we just don't have enough energy that's being bounced back out into outer space because the warm currents are not affording the snow to retain deeper into summer seasons. So finally, with feedback mechanisms, we have positive feedback mechanisms and negative feedback mechanisms. And basically all a feedback mechanism is that it continues a cycle and makes it larger and larger and larger, or bigger and bigger and bigger, if you will, or it changes the direction of a condition. So a positive feedback is like that sea ice. So if you have a little bit of warming, the sea ice is going to melt, which means there's going to be less reflection. If there's less reflection, there's going to be more warming. If there's more warming, there's going to be more sea ice melt. If there's more sea ice melt, there's going to be more warming. If there's more warming, there's going to be even more sea ice melt. So we're amplifying the condition. That's a positive feedback. All right. We can get a similar positive feedback when we add temperatures to the mid-Atlantic and the mid-Pacific Ocean. We're going to then create more evaporation. More evaporation means more clouds. More clouds means more reflection. More reflection then means lower temperatures. Lower temperatures then means less clouds. That's a negative feedback. All right. So those are two scenarios in terms of feedback. We could look at feedback with the chemistry of the ocean, with the salinity. When we don't have a lot of melting of ice, then the salinity of oceans is going to be high, which means the temperature of the water is going to be warmer. But as we start to melt more fresh water into sea bodies, the salinity goes down, which means its ability to keep those temperatures warm diminishes, and the sea bodies become cooler. So that would be a negative feedback. All right. So two examples for you there with positive and negative feedback cycles as they affect climate change. All right, guys, hopefully you got something new with climate change in this set, and we've expanded your understanding a whole lot. Talk to me as you need to, and I appreciate everybody who's sending me emails when they want some clarification or if they need to talk about things. If you haven't done that and you are swimming and finding that you are needing more time on this information or clarification, I really do need you to contact me, all right? Talk to you soon. Bye now.